Let's fire his bed. But let's get back into this. So what I want to do is I want to wrap up this intro to hypothesis testing today, and then I want to start into actually constructing our own hypothesis test as well. Because this is great. This is fantastic, and the reason I created this section, and the reason we camped out here for like a week and a half, if you think about it, we've been in this section for a week and a half, right? The reason is because I want you to know what a p-value is. That's the big new thing. Confidence intervals, boom, totally fine. But confidence intervals are great only for estimation. How's Obama doing? How's he not doing? How's Congress doing? Is Congress really less popular than syphilis? I mean, that's the kind of questions that, right? Those are the kind of questions confidence intervals help you answer. But p-values are kind of used interchangeably from time to time. So I want to make sure we understand what those p-values are. All right, and that's what the quizzes will post. We'll post this one and also one more for next week for you guys we'll do. But here's the deal. We left off last time. We'll come back into that p-value bit in a minute. We left off last time with the ways to be wrong. Do you remember why we could be wrong? You can say no, of course, because it's been 2 days and you're thinking about the exam right now. Why could we be wrong?
False positive. Right?
Thank you, Eric. Perfect. Here's the deal. We get a small p-value. This is one of two things that can happen in a hypothesis test. You can get a small p-value, you can get a big p-value. Rule, please define small. Good study. You're thinking that, right? You're thinking definitions, all about definitions and statistics, right? You're saying small. Tell me what small means, Cassie Moore. Under 5%. That's what small is defined as in here. Why do we use 5%? What is 5% tied to?
95.
95% confidence. 5%, do you remember the word that we use for the 5%? The Greek letter is alpha. But it starts with an S, 5%. It's okay if you don't, we'll come back to it. Say it. Significance, there it was, Jack. Significance, test of significance. Standard deviation is the number of standard errors we go out, and it's tied to that, of course. But 95% confidence in the interval ties to 5% significance outside of the interval. Just get used to hearing those. I'll keep saying them over and over again. So, if you get a small p-value, as a researcher, are you happy or are you not happy?
Are you happy?
You're happy. Why are you happy as a researcher? What did you just find?
You showed something in your study, something different than what previous studies have
Boom! Oh, that was perfect. You have found something in your study that was unusual. Unusual meaning, what do we call those in 243? Unusual data points?
An outlier.
You found an outlier. You found an outlier. So, as an example, hang on a second, right here, okay, the secondhand smoke article, from 0 to 1 hour, we noticed that lung function parameters were significantly reduced. What did we go into the study assuming was going to happen? That secondhand smoke? What do you always go to a study assuming is going to happen? Whatever you're interested in studying, you're going to assume what kind of effect that's going to have.
No effect.
No effect! You go in there saying, you know what, breathe as much smoke as you want, your lungs are going to be fine. And that sounds dumb. But that's what you go in believing. You go in believing that nothing is going to change. And then you act pleasantly surprised when you discover it does. It does. So if you're expecting this bell curve, which is lung function, and you're expecting it to be in the bell curve, right? Look back to your diagrams from last time. In the bell curve, if you get a p-value less than 5%, remember where Eric drew his asterisk last time, that means it's in the tail. That means it's a what? If it's in the tail,
Outlier.
it's an outlier, which means it's unusual, which means it's not what you were expecting. Now here's a question I have for you guys. I'm going to back up rapidly here. I apologize for the speed. I need to find a graph real quick. Back. No, hold this. There we go. Right there. So you got yourself a bell curve. Here's where you're expecting your data to fall, and it falls out here. The conclusion if it falls out here is what? If it falls out here,
Small p-value?
small p-value, absolute small p-value, so you say something's changed.
So it's significant.
So it's a significant change. Exactly, it's a significant change. This is the equivalence of not having confidence intervals overlap each other. That's the equivalency. If you're thinking of confidence intervals, they're not overlapping. Which means if they're not overlapping, where does he most likely belong?
another graph.
Thank you, in some other curve. Now, do you hear how I said that? He most likely belongs in some other curve. Did I say it's guaranteed that he's in some other curve? I said it's most likely that he's in some other curve. Is there a chance that he's in this curve? Of course there's a chance. What is that chance? Exactly what is exactly what is that chance? There it is. It's 5%. And it's 5% because that's the line you're drawing in the sand. And you're saying, if I get a p-value less than 5%, I'm saying, you know what? It could be in this curve, but it's more likely somewhere else. But you're going to be wrong 1 in 20 times. Cassie, you said it 1 in 20 last time. You said that fraction. I said, what's the chance? You said 1 in 20. I said, hells yeah. Because 95% of the time, you're going to land over here if you belong in this curve. 95% of the time, if heart rates don't change, if lung function doesn't change, if breast cancer rates don't change, you're going to land in the curve you were expecting to land in. But 1 in 20 times, you're going to erroneously pop out here. So you can be wrong with a small p-value. And what type of error was that? Do you remember?
Type 1.
That's your type 1. That's your type 1 error. And we call it alpha. And I say it's usually 5%. It will always be 5% in any problem I ask you to do because the world uses 95% confidence, almost religiously. And there's a reason for that, which we'll get into as we go through the course. Your textbook, for whatever reason, loves to mess up with 92% and 98%. So all you got to remember is that guy right there, alpha, is the complement of confidence. So if they're at 92% confidence, what is alpha? 8. If they're at 97% confidence, what is alpha? 3. Exactly. So, what's a logical question? If confidence is the complement of significance, which means confidence is the complement of alpha, and alpha is the chance of being wrong, what's a logical question we can ask then? What do you think? If we're at 95% confidence, and we're wrong 5% of the time, and we don't like being wrong, what logically should we do in our studies?
How can you be more confident?
How could you be more confident? Why not test at, say, for example, 98% confidence, 99% confidence, 99.9% confidence, 99.99% confidence, 99%, you see what I'm getting at here, friends? You can never be 100% confident. But why not just raise the confidence level so high that alpha essentially goes to 0. Did you have a question or a comment for that? I thought I saw some movement. Okay. Rose? No, just scratching. I'm sorry, interrupting perfectly good stretches over there. I apologize. The question that is very, very loaded right now, but I will get into it, I promise you, on Tuesday. But here's the quick answer. The problem is when you get a large p-value, you also have to consider that possibility. Now, you will not get both a small and a large p-value. That can't happen. You get one p-value. If it's small, it's under 5%. If it's large, it's over 5%. Okay? So if it's large, what happened? What happened if the p-value is big? Nothing happened, or at least nothing unusual happened, right? Something happened in the study, but it wasn't anything different than what you were expecting to happen. So you were expecting that caffeine wasn't going to lower heart rate, and guess what? It didn't lower heart rate. You were expecting that secondhand smoke was not going to affect lung function, and guess what? Did it? If the p-value came back big? No. It stayed exactly the same, or arguably not statistically significantly different, which is essentially the same. Fair enough so far? So when you get this, you say nothing changed. But here's the question. What's the chance that you're wrong? Don't answer that. Could you be wrong? Could you be wrong with this? Do you remember the drawing from last time that showed this? Well, would you mind throwing those lights on back there real quick? Thank you, sir. All right. So, I'm going to call this the null curve. That's okay with you guys. I'm going to call that the null curve. And the reason I'm calling it the null curve, I'm going to try to kind of drill that word null into your head over the next couple of days, because that's the hypothesis we're going to be testing as we go through the remainder of the course, the back 6 weeks. And there is this beautiful cutoff range on that null curve, which is usually 5%. Usually keep it at 5%. And if we land out here, like Eric so tactfully drew last time, what do we say? What do we say if our data landed out here?
We found something new.
We found something new, something changed. And what kind of p-value do you have in that case? Small. Beautiful. But we're not talking about that right now, are we? We're not talking about that. Right now, we're talking about what if you get a big p-value, which means you land out here. Or somewhere out there. I don't exactly know where. Somewhere out in that curve. What do you say now? What do you say? Informally.
It goes with the null.
It goes with the null hypothesis. If you talk about like traditional stat speak, we fail to reject the null, which I like going with the null better. There's no reason not to believe it. Did anything change? Everything's exactly the way it was. So you're making the claim based on this data that it looks like we should be here. Could you be wrong? Could you be wrong? Of course you could. Because maybe something changed and you missed the change. So for example, suppose the change was up here. Just to throw out a completely ridiculous example. But suppose that data actually lies on this curve, which would be statistically significantly different. Very little overlap of curves. The average is way up here versus the average being down here. Now, is it likely that the data is out on that curve? Is it likely? It's not likely, but it is possible. And in order to calculate that possibility, you'd have to know where this bad boy fell on that curve. And this is the tricky part, and I don't want to get too far into this right now. We'll have a nice big fat diagram to look at next class, which we'll get into. But here's the problem. Why can't we just say, oh, it's 5%, oh, it's 6%, oh, it's 10%? Does anybody know the answer to that right now?
We don't know the average for that other curve.
Ah! We don't know where this is. We could be wrong if the average is significantly different than this average. Do we know this average?
Yes.
Yes. That's the power of hypothesis testing. You know where your baseline average is. You know what lung function is without secondhand smoke. You know what breast cancer rates are without green tea. You know what a heart rate baseline measurement is without caffeine. You know what Congress's approval rating was before the shutdown. Right? You know all those things. What you don't know is what it is right now. What you don't know is what heart rate is once you pump caffeine into somebody. That's what you're studying, correct? So you're comparing whatever you get back from your study, you're comparing it to this green curve. And it lands somewhere on that green curve. This green curve goes on forever, right? Goes on forever. It's going to land somewhere on that green curve. The kicker is you don't know exactly where. If it lands here, yeah, it's way more likely to be in the green curve than the blue curve, but there's still a chance on the blue curve. The problem is we don't know what that chance is because we don't know what that average is. We have a solution for that, I promise you, but it's a little too tedious right now. I don't want to get into it. Just contextually, keep that in the back of your mind for right now. So, well, if you don't mind killing the lights, that'd be awesome. Thanks, Fred. When I ask you, what's the chance of this? By the way, if you were wrong, what would you call that conversationally? A false what?
False negative.
Wouldn't it be a false negative? Because you said nothing changed. That's like having Lyme disease, going to the doctor, taking the Lyme disease tests, and the test coming back negative. You have the disease, but it missed it. Right? You don't often hear about false negatives, especially with things like drug tests. Right? Or DUIs. You don't hear about false negatives. People get upset with false positives, because a false positive test result is a lot more life-altering than a false negative, obviously, in those cases.
Well,
in those
normally
cases.
you're testing for things that are really negative in general.
Right, like a disease or a drug presence. Yes, you're testing for a negative thing. It's like you're testing for gold in your hair. In which case, you want a positive test result. Gold in your hair. Sorry about that. I don't know what the hell that means. So yes, you're looking for gold in your hair. Whew, it's almost poetry. When I ask you what the chance of a false negative is, what are you going to tell me for right now? You don't know. Because there's no way of knowing what it is until we make some assumptions about that other average. So for right now, here's what you're going to write down if I ask you for the chance of a type 2 error, which is the chance of a false negative. For right now, you're going to call it beta. Why are you going to call it beta? Because type 1 is called alpha, and let's just go in alphabetical order. Why not, right? Let's be logical. That's what everybody does anyway. Power testing, which we'll get into in this class in a little bit. It's one of my favorite things to do. Ties into sample size. should just think about it. It relies heavily on beta. And you'll see, I don't want to talk about it right now. I want to make sure we understand hypothesis testing before we get into basically the hypothesis test that determines that. But here's the big takeaway, and you don't have to believe this right now. You don't have to. I'll hopefully drill this into your head on Tuesday. As alpha gets smaller, beta gets bigger. And that's the quick and easy and probably not believable answer to why not just increase confidence and shrink down alpha. Remember how confidence and alpha are complementary? So 95% confidence is 5% alpha, 5% significance. 99% confidence would be 1% alpha, 1% significance. The problem with shrinking alpha, i.e. making confidence bigger, you're also increasing the chance of a false negative. Now that probably doesn't make any sense to you right now, and I hope it doesn't. If it does, bless you. Become an actuary, please. If it doesn't make sense, don't worry. On Tuesday, I'm working on making it dynamic, and I hope I can do it between now and Tuesday. Fingers crossed. If not, I have a beautiful static image that'll explain to you why that has to be the case. It has to do with the central limit theorem and other things, which is beautiful. I think it's beautiful. Don't just think it's Tuesday morning. Fair enough? Do we see any potential type 2 errors in all those wonderful research studies I gave you on a handout? Do we see any potential type 2 errors? Hell yeah, you did. Say it with me.
Aren't they all potential type 2 errors?
Not with small p-values.
Oh.
With small p-values, you cannot make a type 2 error. Why can you not make a type 2 error with a small p-value? It has to be a type 1 because it's a positive test result. A big p-value is a negative test result. So you can't be false positive with a negative test result. Does that make sense? And I'm going to break this down with your card trick data again momentarily. But for I know, Kelly, it's throwing. It really is. So here's one of the ones we could have potentially made a type 2 error on. Remember this one? After 3 hours, once in the Greek study, we stuck a bunch of people in a room, made them breathe smoke for an hour. We noticed that they couldn't breathe anymore. They couldn't even stand. Then after an hour, we said, get the hell out of there. Took them outside, put them back on the island of Crete, and said, breathe this beautiful ocean air. 2 hours later, we measured them again. And what happened to the lung function after 2 hours? Back to baseline. So the conclusion is that after 2 hours, outside of the bar restaurant level smoke level, percentage, whatever it was, lung function parameters were not reduced or back to normal. Could we be wrong? Of course we could be wrong. Of course we could be. How could be wrong? I said, define this type 2 error in context. I'll give you a hint on this one. The previous one I had you do in context was the 0 to 1 hour. I'm going to back this up just a smidge. Just a smidge. Just a smidge. Okay. This was the 0 to 1 with the small p-value. I said, define this error in context. We know it's a 5% chance of it happening. But here's what it would be in context. With a small p-value, our claim is that secondhand smoke from 0 to 1 hour reduces lung function. That's the claim. If we're wrong, we put a comma after that, and we finish it with when in fact it doesn't. That's a false positive, right? We're saying it reduces lung function, but it actually didn't. That's the potential type 1 error. With me now? Okay, you guys ready? Define for me the type 2 error that could potentially exist here. Let's give it a whirl. Wake up now. Go, Drew. Love it, baby.
Gave him too much time.
Oh, you're trying to give me a reason for the error. Don't overthink it. Just state what the error could be. Thank you for that. Maybe too much time. If we had 1 hour, it'd be different. Good. Just, Danielle, go.
When in fact too much time? Or when in fact it does?
Good, good. I was looking for more general, Drew. You're looking for reasons. Danielle's giving us this general. Our claim is right here. Most lung function parameters were not reduced, comma, when in fact they were. When in fact they were reduced and we missed it. See, our tests can always miss the truth. And the problem is we don't know what the truth is. All we have is study after study after study, replication after replication after replication. Part of which we're getting at in this class already, and we're going to continue to get at that. But we can miss the parameters. It's possible that we miss it. But the more studies you see, the less likely it is that they're all missing it. If every secondhand smoke study comes back if every single secondhand smoke study comes back, that's done the same way, in a reliable, believable methodology, and they're all saying that secondhand smoke, they're all saying that secondhand smoke is bad for you, but via lung function parameter measurements, what's the chance they're all wrong?
Really small.
It's got to be really small, right? Because the chance that every single one of them is wrong with a type 1 error is 5%. 2 that are both in error is 5% squared. 3, 5% cubed. 4, 5% to the 4th. You see what I'm getting at? So every study comes back saying it's bad for you. If they're being replicated, the chance of them all being wrong shrinks to 0. So when you read a study that contradicts all the other studies that have come out, don't believe that that disproves anything. That could just be one study in 20 that's in error. You see what I'm getting at here? I read an article, it's been a while now. It was called The Truth Wears Thin or The Truth Wears Out. I hyperlinked it in the Stat of the Day blog back a few months. I think you can do a search within the blog. And all it did was it reported on a whole bunch of studies that had been overturned. So a study came out and said, you know, gold hair in your belly button implies some kind of advanced risk of grade 3 melanomas, or I don't know, I'm making crap up now. And one study showed that. And then it was later found to be an error. Well, of course that's going to happen. 1 in 20 studies have to be wrong by the definition of what a type 1 error is. You see what I'm getting at? Not every study is right every time. If they get overturned, that's part of the statistical process. That's why researchers keep their jobs when they don't find anything sometimes, or if they find something that then turns out to be false. You see what I'm getting at, friends? Now, if you're wrong all the time, then we got to talk about what the hell you're doing or what you're not doing. But it's okay to be wrong, because being wrong is part of the uncertainty. Why this course is called probability. Yeah? Okay, now what I wanted to do, you're going to have this entire, like I said, you're going to have this entire spreadsheet available to you. The takeaway you're already going to have in your spreadsheet. These are the big takeaways. The big takeaways. This is basically a wrap-up of what happens and how you can be wrong. It's the very last page of your assignment there. What I want to do with the remaining 12 or so minutes that we've got is analyze our card trick from day 1. When I said, as soon as somebody pulls a red card on this deck, you guys can get out of here. I want to go back to that. Okay. I want to go back to that. I want to see if you guys can see how that actually applies to this. With me so far? Okay, hold those thoughts. Let's fire this bad boy up. You might remember this from the very first day. I walked around. I had how many people pull cards? How many people pulled cards out? 5. How many red cards did we get? 0. Rachel's not here today. After the second red card, I believe, came out, she started crying foul. We're going to talk about the potential of a type 1 error is exacerbated in that case. She actually had a 20% type 1 error probability. You'll see what I'm talking about momentarily. But I think everybody in here, somebody demanded to see the deck. Who was that? Was that Eric or Michael? One of you guys said, "Can we see that deck?" Yeah, can we see that deck? And it was a 4th or 5th card, I think. You were like, "Let me see that deck," because I think something's up. Good. And you guys had a claim the deck was rigged. Well, here's the problem. The deck is or is not fair. And you don't know that, and I'm not going to show you the deck because I'm a bastard. Okay? But that's the truth. This is the thing. This is the thing. These are complementary, completely opposing realities, neither of which you know the likelihood of. Well, I shouldn't say that. You do. One of them is 1 and one of them is 0, but you have no idea which one is which. One of those two things is true. Now, clearly, when I held a deck of cards up for you guys, what did you assume about that deck of cards?
Fair.
You assume it's fair. I mean, otherwise you go through your entire life as a skeptic. I think you're trying to pull something over on me. You're in Vegas, dude. Right? It's not, you know, you assume the deck is fair. You assume a coin has a head and a tail on it. You assume your car is going to start when you put the key in the ignition. There's certain things that you just you assume status quos for the most part in your life. You're kind of used to patterns, you're used to experiences. So you assume that. By the end of that day, you were leaning towards this, right? But that doesn't matter. You still don't know which one is true. All you know is you had data. Okay, so here are the claims you could make based on that. Here's the claims you could make based on that. Either you say the deck isn't fair, or you say the deck is fair. And what we went through on that first day of class were the 4 possibilities of what could happen. Either you say the deck isn't fair, when in fact it is. That's a false positive, isn't it? Because when you say the deck isn't fair, that's a positive test result. You're saying, you know what? The deck actually is okay, but we got deviant data. So that's a problem right there. But if you say the deck isn't fair and the deck is not fair, like, you're right. Problem is, you don't know what that is. You don't know what that is. As a matter of fact, there's no way of knowing what this is. Excuse me, what this is there? Because in order to know what the value of this is numerically, what's the value of this? What's the chance here that you're wrong? Always. Assuming 95% confidence, 5%. It's 5%, right? It's 5%. What's the chance here? Trick question.
How can you not know that?
Because if the deck isn't fair, you have to know what percentage of the cards in it are actually black. You see, here's the trick. You guys pulled 5 black cards out of the deck, right? And you calculated your likelihood of it not being fair based on the fact that it was fair. How likely is it to not get any black cards out of a deck of cards? Or excuse me, not any red cards out of a deck of cards, doesn't matter. The problem with this is, if you don't know how many black cards are in the deck versus red, you can't do probabilities. Fair? Is that fair? Okay, good. So this is pretty much the only thing that applies to you guys from a deck of cards example. We didn't say the deck was fair. Did anybody in here think the deck was fair at the end of that day? You're like, oh yeah, it's fine. He's got 5 black cards, whatever. Totally fine. Pull another one. Maybe it's red this time. Was anybody thinking that? No, because you wanted to leave. You wanted to get the hell out of here. So nobody was even claiming this. So we'll come back into that on Tuesday. What I want to do is I want to kind of walk you through the derivation of a p-value as you guys did it that day. Check this out. Here is what happened after the first person pulled the first black card. This is a binomial distribution. If you pull a black card, if you pull a card out of a deck of fair cards, half the time you're going to get a black card, and half the time you're going to get a red card. Does that make sense? The problem is that if you get a red or a black card on the first pull, who cares? It's 50-50, correct? So nobody thought anything was weird at this point. Everything was fine. Everything was fine. You're like, pull a black card, try again. The next person tries. That is what the distribution looks like now. What I've done over there in red, that red column, is what you guys kept seeing. That's what you guys were experiencing. So after 2 cards, and we pulled 2 black cards, I told you, Rachel freaked out at this point. She's like, next read! Well, what's the chance of pulling 2 black cards out of 2 pulls if the deck is fair? 25%. Why is that unusual? 25%, it's going to happen 1 or 4 times. It's like having 2 kids and having them both be a boy or both being a girl. Actually, both being a boy. If they're both being a boy or a girl, 50%. So how many families do you know where there are 2 boys? And there's 2 kids, and that's exactly. A lot of us know a family where there are exactly 2 boys. It's like, okay, we got that. So we pull a 3rd card. We pull a 3rd card. Now, we're still in this bar, which only happens 12.5% of the time. So it's less likely that we keep seeing black cards. But it's still not crazy. But now, when you start pulling 4 and 5, that's when we start saying, okay, we're getting so far away from what we should have seen. Because on average, you should be seeing the middle of these curves, right? On average? On average. So with 1 card, you should see half a red card. With 2 cards, you should see 1 red card. With 3 cards, you should see 1.5 red cards. With 4 cards, you should see 2. With 5 cards, you should see 2.5 red cards on average. On average. We saw 0. And all of a sudden, you can almost... Who said standard deviation earlier? Was that somebody over here, Rosie? I think it was you, right? All of a sudden, you can see roughly where 95% of the data should be. And this is the first time we're actually out of that range. And this is where you go, I believe something is up. I believe something is up. I believe there's something afoul here. That's the idea of a p-value. Now, what is this whole curve built on? What's this whole curve built on? The assumption that the deck is fair. Cassie, your question about why we can't check the true negative is because here's the data point we got, correct? If your claim is that the deck isn't fair, that means you have to build me a second curve that's somewhere down here that has too few red cards on average. The problem is, where down there? You have to make a claim. oh, I think there's only one red card for every 3 black cards, or one red card for every 2, not 1 for 1. And that's why beta, that chance of a false negative, is so tricky, because you have to know where the other curve is, or at least set up some examples for it. We'll get to that in a couple weeks. Yeah? I just realized too, this should be number of red cards, not black cards. I apologize for that stupid typo. It doesn't matter, it's the same logic because it's symmetric, but we were looking for red cards and we weren't getting any. But I'll fix that before I upload it for you guys. Yeah? How you feeling? Feeling alright? Ready for your 10:15 class? Hell yeah you are. Okay, here's the thing. You got your take-home due on Tuesday. Bring questions on hypothesis testing too. Before I move into actually, I have a hypothesis test ready for us to go on Tuesday. But before we do that, I want to make sure you understand what p-values are. Inside, outside, left, right, up, down, innie, outie, gold-plated navel hair, whatever else you need. All right? And have a good weekend. Rosie, go!